the recording. Let me let people enter like this. Okay. And let me also so good morning, good afternoon, and good night, and welcome to this webinar of the Technical Talks of CTSoc series. As usual, I'm gonna make a quick introduction to the talk. And by the way, I have seen that also Dixon Lin, who is the vice chair of this technical committees of CTSoc, has joined it. Well, maybe this will be one of the last time that I make this introduction. And so it's a pleasure for me to welcome you to this talks, which have been launched within the technical activities area of CTSoc. CTSoc is the acronym of IEEE Consumer Technology Society. It has, like any IEEE society, a number of areas like publications, conferences, educational activities, industry and standard, and technical activities. The technical activities are including the technical committees, which have been launched now since more than 5 years. It was end of 2024. In January 2020, December 2020. In January 2021, 14 technical committees were established, and then one was added. And these are the 15 technical committees that, as you can see from the names, are covering basically the broad spectrum of consumer electronics and consumer technologies. These technical committees, together with the future directions committees, are overseeing a number of activities that are carried out within CTSoc. And well, this area is chaired by myself with the support of Professor Dixon Lin, and it is coordinated by the Technical Committees Board, which is participated by CTSoc President Fabrice Labeau, Vice President Conferences, Professor Fawzi Beman, Vice President Publications, Professor Norbert Eringsar, and Vice President Industry and Standard Activities, Mr. Michael Condry. And within this technical committees board, we have the officers, so chairs, vice chairs, and secretaries of the 15 technical committees. These are the newly elected officers for the technical committee. So within these technical committees, initially there were technical talks taking place from time to time at the technical committee level. At a certain point, we decided to transform these technical talks in something broader, inviting every month or every 2 months 2 speakers from 2 different technical committees to share their research with potentially interested colleagues. If you don't know the details of the technical committees, you can go to this page and you will see that each technical committee has its officers, at its mission and objective. It has its own list of members. And you can join, if you are not yet a member of the technical committees, you can join. There's a form that can be filled in. And so far, you don't need to be an IEEE member or CTSoc member to join the technical committees. You can simply fill this form in, and you will become part of this family, and family that is doing a number of things in the areas of consumer technologies. This slide is not the most updated one, because we have more than 1,500 members now in the technical committees, and these members are growing and growing and are supporting our technical activities areas in many ways. So they are supposed to help with conferences, with publications, with standards, with educational activities, with history activities, and they are periodically meeting, and they are providing names of people willing to volunteers helping in the organization of conferences, well, if you are really interested in seeing what are the outcomes of activities did so far by the technical committees and opportunities created for the members of these technical committees, you can check the page outcomes and opportunities under the technical activities tab on CTSoc website. So basically, they are providing names for technical positions in our major conferences like ICC Las Vegas, ICC Berlin, GEM, ICC Taiwan, and stuff like that. And the calls for volunteers are out now. They provided names for covering the associate editor positions of our main journals, like Transaction on Consumer Electronics and Consumer Electronic Magazine. And the boards of these journals are going to be renewed in a few weeks. They are proposing special sections in journals. They are organizing workshops and sessions in conferences. They are involved in a number of activities like the IEEE Digital Privacy, Digital Reality. They are supporting collaborations with other societies like Signal Processing Society, like AES and stuff like that. They are organizing special interest groups like the special interest groups on the metaverse. They are providing names for our distinguished lecturers program, speakers for our webinars and tech talks. They are contributing to funded projects like we have launched, for instance, a call for internship projects, and we have two projects running at this time. We are searching for people willing to contribute at the implementation of standards and stuff like that. This is just one of the activities that I was mentioning, that is the IEEE Digital Reality, in which we are opening and broadening the collaboration to other societies, not just CTSoc, but also Reliability Society, Electronic Packaging Society, Engineering and Medicine and Biology Society, and more. So if you are willing to help, please go on CTSoc website, check the technical activities page, and submit your application. Today we are here because, as I said, we are periodically organizing these talks of CTSoc. They have been very successful. This is the list of talks that has been held so far, but different technical committees. Today, we have two great speakers. They have been identified by the Technical Committee on Application-Specific Consumer Electronics for Smart Cities, SMC+CPE, and the Technical Committee on Consumer Power and Energy, the CPE-TC, Professor Chengxing Lai and Professor Zihong Wang. So I'm going to leave the floor to them and to the officers of the technical committees who will be introducing the two speakers and will be moderating the rest of the webinar. So I stop the screen sharing and I leave the floor to the colleague. We do have today Professor Massimo Conti for the CPE-TC, and Dr. Bunchong Han for the SMC+TC, and other colleagues who joined it. So I leave the floor to them for moderating the remaining of this talk. And of course, Dixon as vice chair.
The first speaker will be from Prof. Lai Shan-Chun, pronounced University of London, the director of his talk shall be Smart Road Transportation Technology for Smart City. Prof. Lai, are you ready to share your screens and your talk? Also, some dimension of Popeye is active member of the Achievement Smart City, as well as the newsletter editors as well.
We cannot hear you very well, Boon Chong, but I think you asked Professor Chung Sing like if
Yeah.
is ready to share. Yeah, okay,
Yeah.
we can hear you very well, but
Oh, sorry.
Okay, thank you, Professor Boon Chong Ang and Professor Fabrizio Lamberti for the kind introduction. So I will now share my screen. Just give me a moment. Okay, so I will try to be on time. So about 15 minutes, so about half past. So thank you very much for the kind invitation. And I worked with Boon Chong on smart cities activities widely, including the smart cities communities publications activities, and of course also the consumer technology smart cities TC. So for today, if the attendants can please mute your speakers. Yeah, thank you. So for my today's talk, it will related to intelligent transportation in smart cities. So I'm from Brunel University London, which is a UK university based in central London. So for my talk, it will cover three main topics of interest, which I think is a quite hot topic these days. So one is related to the airport shuttle buses. So of course, in the airport, a lot of passengers and consumers, we need to travel using shuttle buses. And within the smart cities, we will including different kinds of EVs, electrification techniques, like wireless charging. And of course, wireless charging is still a rather research kind of a technology where a lot of charging happens using conductors or cables. So we look at the techno-economic prospect of using airport shuttle buses with wireless charging. The next area of work I've been working on is the energy management for large-scale energy storage systems using with EVs as well. And then finally, I want to talk about in the future, we have something called the eVTOL technologies, which stands for the electric vertical takeoff and landing aircrafts. So today we have a lot of transportation rely on the road. Doesn't matter if it's vehicles or railways. However, we still have some sky, or we can use the sky to make some short journeys from different cities and areas. So as I mentioned, transportation is a key part of a smart city. And in today's world, we still suffer a lot of issues, which is related to congestion and carbon emission. So even taking some data back in 2014, which is over a decade ago, the congestion time and the cost is still very expensive. And of course, since 10 years from now, we have made a lot of progress, including using EVs, which can displace the tailpipe emission. However, there is still a lot of work that is needed to meet the net zero carbon emission targets for many countries. So for example, in the UK where I am, we have a target within 2050 to have a net zero emission community. And this is not very far from now, so it's about 25 years. But we still have, for example, the transportation area that needs to be met. So just to remind everyone, the Sustainable Development Goals, SDGs, are given by the United Nations, and I believe this is something we want to achieve in smart cities. So in the recent years, we have a lot of breakthrough in technologies like smart cities transportation. It's because of the reduction in the battery cost. So of course, battery is not something new. We use batteries in mobile devices, in laptops, but for batteries to be able to store energy, which in kilowatt hour or megawatt hour scale, this can only be achievable if the cost is low enough. So in this case, my paper, which was published several years ago, I was forecasting the battery cost, and now we expect the cost to be about $500 per kilowatt hour as the capital cost, which has been plummeted from $2,000 per kilowatt hour before 2010. So we can actually see that battery is a economic solution these days, which allows us to accommodate renewables and also to facilitate smart cities transportation. So for today's talk, I want to provide some of my research outputs, which is related to consumer technologies. So for example, in energy and transportation, within the smart cities, a lot of EVs can be connected to the distribution networks through home charges. And one of the issues we have from the grid perspective is about managing the distribution networks. So we need to ensure the voltage level is within the constraints, as well as being able to balance the power, which has to be from a second to second basis. So the power supply and power demand must be balanced. So for this work, I put forward a optimization model which maximizes the profit of a big scale or large scale energy storage. And this is used for the fast EV charging infrastructure in distribution network. And the solving algorithm for this maximization problem is used with the reinforcement learning algorithm. And we actually compared with the state-of-the-art algorithms, including heuristic methods, which shows that the TD3, the twin delayed approach for reinforcement learning is superior. And we also validated using some of the UK data as well in this part of the study. So this table comes from the paper, and we can see we actually compare to several references as part of the work, which relates to the profit maximization of the large-scale battery in a distribution network. So we are one of the few papers that employ the reinforcement learning approach. In particular, we adopt and revise the TD3 algorithm, which considers the smart charging issue. And we actually conducted a in-depth analysis of the cost of storage and the investment rate of return as well. And of course, we consider renewable energy. So this is actually the problem statement where we have the large-scale battery at the bottom, and on the left and the right, we have the renewable power generation, which is intermittent, including solar energy. And on the right, we have the EV charging stations, which takes high current, of course, EV charging if it's rapid charging. And we have a lot of kind of vehicles from the consumer side. And this all can be connected to the distribution network under one node. So in terms of the management, this is a highly uncertain and non-linear problem because the renewable power generation, as I mentioned, is uncertain, and the EV charging can be uncertain as well in many cases. So one of the dispatchable sources within the network is the large-scale battery in this case. So this is all connected to the distribution network, and we can see we have the power flow as well as the information flow. So the information flow allows that the battery can make decisions based on two things, the charging and discharging, of course. So one question some people may ask is if we have a lot of EVs, then EVs itself has the battery capability, then what is the purpose of having the big battery in the system? So there are two reasons, as I mentioned. So one is the plummeted cost of the big battery, so it makes investment viable. And the second reason is because for the EV charging, the decision to grid to vehicle or vehicle to grid, where this is discharged to the grid, is mainly dependent on the consumers. If the consumers do not want to discharge to the grid or charging when there is a surplus of renewables, then consumers can they can choose not to do it. Of course, we can incentivize them using good tariffs or cheap electricity, but at the end of the day, it is up to the consumers to make the decision if they want to support the network or not. So this is something that is rather uncontrollable as well in many cases. So this is the reason for the big battery in the system. So of course, in different countries, they have different ways of managing the energy storage within the network. So for example, in the UK, where I am from, the battery cannot be owned by the distribution network. So for example, UK Power Networks or SSEN, Scottish Southern Electricity Networks, those are typical companies of the distribution networks in the UK. So the big battery has to be commissioned, managed, and owned by a third-party company. So this is why the profit maximization is an independent problem within the network. So the profit goes to the third-party company. So of course, if there is a profit, there could be a choice to invest. If there is a loss, then of course the third-party company will not support this kind of projects. So on the right, we can see the battery degradation model is also included in this kind of problem for a more precise and more real study. So this is the solution algorithm, which takes the data from the historical, and we also augmented the data, including a forecasting model, to build a larger data set. And this is trained within the power flow problem, which the power flow problem acts as an environment for the distribution network. And we can actually say that using the reinforcement learning, the battery will decide to discharge or charge based on the rewards function. And of course, the battery aims to maximize the reward based on changing the states. So the online implementation uses the real data. So this can be real-time data, and the reinforcement learning is expected to do the real-time decision for the battery. So this is some of the results we have for this work. So on the left, without the battery energy storage, as we can see, during the midday, there's a lot of solar energy, and in some cases, it could violate the voltage profile within the distribution network. So we have the upper bound voltage and the lower bound voltage. So this is one of the issues with, for example, with a surplus solar energy in the system, and the EVs, they are not participating in vehicle to grid or grid to vehicle activities. And on the right hand side, we see the solutions based on implementing the reinforcement learning approach, and we can see the voltage profile on the right, which now within the constraint, as we can see. And we can see the battery state of charge, as well as the power for the battery charging and discharging. Negative means it's charging during the peak times of the solar energy. So for this work, we made a detailed economic assessment of the big battery energy storage. So typically we can use the net present value. So the net present value is talking about the investment of the battery. If it's a positive number, then this can be a viable option to the project. If it's negative, that means the project does not worth to invest in. And the net present value is highly dependent on the discount rate, which is the weighted average capital cost at the x-axis. So if the discount rate is high, then in several cases, even with the superior TD3 algorithm, we can see that it may not be appropriate to invest. But if we have a lower discount rate, the TD3 scheduling algorithm for the battery can be profitable. And this is much better than, for example, the DTBG reinforcement learning algorithm, and also some of the traditional or more conventional optimization like the PSO and simulated annealing techniques. So on the right-hand side, we can see the cost of storage for the battery. And again, this is a similar issue. If the cost of battery is too high, then it may not be worthwhile to invest. It may be better to charge the or to supply the energy using the retail price. So the second work recently, which I've been working on, is called the economic assessment of the wireless charging for airport shuttle buses. So as we know, airport shuttle buses, they are used greatly for transporting passengers from the terminals to the airport directly, or vice versa. And in smart cities, in many cases, this can emit a lot of carbon emission because the buses are run by petrol or diesel engines. So this work, we're trying to understand what is the economic prospect in using wireless charging for this EV shuttle buses. So I'm not going to talk about what is wireless charging in detail, but wireless charging, essentially speaking, is we have the ground and we have the vehicle. Both of them, they have some kind of coils, inductors, which allows the coupling of the field, which allows the transfer of the energy between the vehicle and the ground. So there are many technical issues that has to be addressed in this day and age, including charging during the dynamic situation. So the coupling may not be good. And also the ground also is the infrastructure. If there is some damage to the ground, that could affect the efficiency as well. So as I mentioned, wireless charging for vehicles is still quite a lot of work that needs to be done as well. So for this work, we consider the airport system or the transport network, as well as the bottom, we have the power network or the distribution network. So we need to charge the shuttle buses at different times, depends on the airport demand in terms of the scheduling flight. And we use the agent modeling technique to model the agent. So for example, the shuttle bus and the flight agent, when they can do the different activities. So in this problem, we formulate the optimization problem, minimizing the charging cost for the wireless charger, as well as the battery cost. So we use the AnyLogic to simulate the agents, which talks about the location of the shuttle buses, particularly. And we use MATLAB to perform the power flow analysis, which tries to minimize this objective function. So here we see the right is the demand of the flights. So at different hours during the day, we have different flight demands. And on the left-hand side, we actually adopt a real life airport network for the London City Airport. So we can see the transformer or the distribution network is in the blue line, blue shaded area, and the location of the airport or the flights can be within the base as shown in the yellow. And in this work, we consider 4 case studies. So from the conventional diesel shuttle buses to the shuttle buses, EVs, with the bidirectional wireless power transfer and the power supply unit. So I'm going to the results directly because of the time concern. So we can see that after using the wireless power transfer for the shuttle buses, the voltage profile within the distribution network is much more stable. So in the morning, there is a dip if we use the traditional cable charging because the shuttle buses, they are not used in the morning. So this is when they are charged. However, the charging will draw a lot of the current, which includes a plummet or a dip in the voltage of the network. However, if we use the wireless charging technique, we can actually provide a rather consistent or stable voltage level, which shows with the case 4 and case 3 in particular. And on the right-hand side, we can see the comparison of the different cost of the charging. For example, in case 1, we use the diesel shuttle buses, which includes the fuel cost only, so there's no electricity cost. But on case 2, 3, and 4, in particular, we can see there's a reduction in the cost of charging the EVs. However, we still need to consider the actual infrastructure cost for the wireless charging as well, in terms of the repair, as I mentioned, for the roads, etc. So some of the future work includes looking at the reliability of the system and even installing a big battery in the airport, which is similar to the previous work, which can support the network operation. So this is all for today's talk from me due to the time. But before I complete the slides, I just want to share a news that recently I published a book with the Wiley IEEE Press, which relates to smart city in terms of energy, transportation, and health. So I welcome for you to read this book, and I believe it's quite relevant to the smart cities technical community. And I do have some complimentary copies available in PDF if you want to understand more about this book. So that's all from me. Thank you, and thank you, Boon Chong.
Anyone? Any questions about offline? Thank you for offline and can you also have your contacts listed so that those who would like to have a complimentary copy of these books also can reach out to you?
Yes, of course. I'd be very happy to have further discussions offline. I mean, collaboration or any feedback to my research, I really appreciate for that. And I can also make available the slides for you, Boon Chong, and you can circulate to the attendees today as well.
Okay, thank you.
Thank you.
Then shall we have our next speakers? So the CPE chairs introduce the next speaker.
Okay, thank you. My name is Massimo Conti. I'm the chair of the CPE section. So I will introduce the next presentation. I asked to Professor Zikong Wang to share. Okay, perfect. Thank you. Professor Wang is a professor on the South China University in China. He received a master degree in Huazhong University in China, and then he is associate professor in Guangzhou in intelligent engineering in the South China University of Technology. So his research interest includes the wireless power transfer, resonant power conversion, and artificial intelligence in the field of power electronics. So thank you, Professor Wang. I leave you the desk.
Yes, thank you, Professor Conti. Just as Professor Lai mentioned, that wireless power transfer is not that good nowadays. So my talk, the topic of my talk is optimized design of anti-misalignment magnetic coupler for static and dynamic inductive power transfer. Okay, allow me to give a brief self-introduction. I'm an associate professor in South China University of Technology, which is located in the Big Bay area of China. So Big Bay area, this is Hong Kong. I achieved my PhD degree here, and later I worked as a postdoc in Macau, and then now I'm working in Guangzhou. So this is the Big Bay area in China. Okay, this is the outlines of my talk. It includes 3 contents. Okay, so let's see it's the background. The background is wireless power transfer used in static and dynamic EV charging. So anti-misalignment magnetic coupler is most essential in wireless power transfer. It means that we want to transfer the power we want to achieve a constant, a stable power transfer. We need a magnetic coupler, which is misalignment tolerant. And nowadays, this kind of magnetic coupler is widely studied and used. We can see this photo. There are 2 coils. One coil is responsible to capture the horizontal magnetic flux, and while the other coil is responsible to capture the vertical magnetic flux. So when there is a misalignment, one coupling decrease while the other coupling increase. So these two coils operate in a complementary way. So we can maintain a constant magnetic coupling in this way. And this kind of this structure of the magnetic coupler is widely used, but is it good enough? We don't think so. We can observe in this figure for this coil, it occupies a very large area to capture the horizontal magnetic flux. So it takes a lot of copper usage. Okay, the copper usage is very large. So in our first work, we want to optimize the copper usage of the magnetic coupler. So this is the traditional the structure, just as what I mentioned. There is double D coil and there is a quadrature coil. Okay, and we propose a new structure, and the new structure is something like this. And there is a rectangular coil, same as the quadrature coil here, the pin coil. And we replace this double D coil with this solenoidal coil. So from this figure, we may estimate that the proposed structure has less copper usage. So we can do some numerical analysis. We build a numerical calculation, and we analyze the magnetic flux capture capability of these two coils, the double D coil, the yellow one here, and the solenoidal coil. And we find that the solenoidal coil can better capture the horizontal magnetic flux using the same amount of copper, which means if we use the solenoidal coil to capture the same amount of the magnetic flux, then we can use less copper usage. Okay, so the proposed solenoidal coil can save about 43% of the coil usage compared with the conventional and widely used double D coil. So and yeah, of course, we build some experimental prototype to validate our proposed structure. And yeah, this is the misalignment, and we can observe that the misalignment is about 50% of the length of this magnetic coupler, and we can maintain a stable output current. And we can also observe that the power transfer efficiency is almost constant as well. The reason is that these two coils, the solenoidal coil and the rectangular coil, they are operating in a complementary way, and the magnetic coupling is almost constant. So that's why efficiency can maintain constant, even though there is misalignment. Okay, left-hand side 15% and right-hand side 50% misalignment, but the efficiency is still constant. So this is the first work. We optimize the copper usage of the magnetic coupler. We can reduce the copper usage, but we still maintain the misalignment tolerance, the anti-misalignment capability. Okay, for the second work, we want to further simplify the control issue. Yes, and yeah, in our first work, we have already proposed a new magnetic coupler structure, and it is based on rectangular coil and solenoidal coil. And so based on this, the proposed structure, we further analyze that, the magnetic coupling is just shown in this figure. We can observe that on the right-hand side, the magnetic coupling is complementary. But on the left-hand side, they are not complementary. What we really want is the mirror of this magnetic coupling, that as the dash curve shows. Yeah, so the dash blue curve and the red curve, they are complementary, but the solid red curve and the solid blue curve, they are not complementary. So what we want is the mirror of this curve. So to achieve the mirror of this solid curve, usually we need some active, we need detection and active control. But we know that it is usually hard to detect the change of the magnetic coupling. It's really hard to do that. And yeah, for the control, we need to take more complex control if we use this way to get the mirror of this curve. So in the second work, we try to eliminate the detection and control. Yeah, without any detection and control, we can still achieve the misalignment tolerance. That's what we want to achieve in our second work. So we first build a circuit model, and yeah, this is just based on fundamental approximation. Due to the time, I'm not going to talk too much about details of the modeling. And we can derive the output of this system, and it is given by this expression. And we can find that there are two terms. For the first term, it is related to the product of two mutual inductance. Okay, so for these two mutual inductance, the product of these two mutual inductance, on the right-hand side, they are positive, but on the left-hand side, they are negative. So they are not isosymmetric. So, and for this term, for the first term, we want to eliminate the first term. Yeah, because we want to eliminate the detection, and but this term is asymmetric. So we want to eliminate in this equation. So to eliminate this term, we can use orthogonal excitation, which means we can set theta to be 90 degrees. And for the second term, it is related to the sum of the square of the two mutual inductance. So for this term, we want to minimize. We want to minimize the fluctuation of this term, and we can design the compensation parameters, C1 and C2. They are compensation parameters. So yeah, in this two by using these two steps, and we can achieve stable output, and we can maintain a stable efficiency. Please note that there is no any detection or active control here. So, which means the system can be very robust. Okay, in our third work, we want to extend the misalignment tolerance from static application to dynamic application. For dynamic wireless power transfer, Professor Lai have just mentioned that. And we can also observe, just as Professor Lai mentioned, there is some fluctuation. Yeah, usually for dynamic wireless power transfer, fluctuation is cannot be avoided. So people usually place the transmitter coils. Okay, here they are segmented, but they place close to each other one by one, and there is no any spacing distance. So if you allow spacing distance between two adjacent transmitter coils, usually the power fluctuation occurs. So in our third work, what we want to achieve is we want to mitigate the output fluctuation, and in the same time, we want to allow large spacing distance. Yeah, we place the segmented transmitter coil in this way, allowed large spacing distance, but we also eliminate the output fluctuation. That's what we want to achieve in our third work. So we propose a new structure of the wireless the dynamic transmitter check. It is something like that. We still use the rectangular and solenoidal coil, the rectangular and solenoidal pad. Because we have already mentioned that this coil can save the copper usage, so we still use the same structure, and we place these RSP, rectangular solenoidal pads, one by one, and we allow large spacing distance. The spacing distance is about 15% of the length of this transmitter pad. And that's one by one. And for the rectangular coil, the arrangement is the same. But for the solenoidal coil, the arrangement is alternate. So for example, this one clockwise, and this one anti-clockwise, clockwise and anti-clockwise. So something like this in this way. And this is the operating principle, and we analyze the mutual mutual coupling between the transmitter coils and the rectanguloids, and something like this. The web curve indicates the let me see. The web curve indicates the rectangular coil to the rectangular coil, and the blue curve indicates the solenoidal coil to rectangular coil. Because in the transmitter side there are two coils, okay, and in the receiver side there are only one rectangular coil. So we found that this is complementary, and this is complementary. So we can maintain stable coupling here, and the same here, complementary, so stable. But for this part, for this region, they are not complementary. What we want is the mirror of this solid curve. If we get the mirror of this solid curve, then it is also complementary. So, but this is not a big problem for us, because in our second work we have already solved this problem without any detection and control. We can maintain constant output. Okay, so the same circuit modeling, and we derive the output voltage of the system, and there are two terms. For the first term, it is the sum of square of the mutual inductance, and for the second term, it is the product of the mutual inductance. So for the second product, we eliminate the second product. We nullify the second product by using orthogonal excitation, and for the first term, we optimize the compensation design, and we can minimize the fluctuation. Okay, so the experimental prototype is something like this, and this is the rectangular and solenoidal pad. 1, 2, 3, and the size of the length is about 300 millimeter, and this is a spacing distance 150 millimeter, 50%. Okay, and we can find that the output voltage throughout the whole range, the fluctuation of the output voltage is within 5.5%, and this is the fluctuation of the efficiency, only 1.2 fluctuation. Okay, that's the key results of the third work. Okay, a brief conclusion. Our recent works propose a low rectangular and solenoidal pad, which is a good approach to misalignment tolerance with reduced copper usage. And based on this, we develop a passive scheme to excite the proposed structure of the magnetic coupler without necessity of using detection and control. and we further extended the proposed magnetic coupler from static to dynamic wireless power transfer scenario. So if you have interest, you may check these papers, and more details are included in these papers. Okay, so finally, allow me to do a advertisement. We have some openings for postdocs, and of course, you are all welcome. I'm looking forward to cooperate with you. Okay. Yes, that's all my presentation. Thank you very much.
Thank you. Thank you very much. Now it's open for questions. Any questions? Just to break, I have a question. So I see that the efficiency is 85%. Is a good, but do you think it will be an improvement in the future?
Yeah. Thank you, Frank. This is a very good question. The efficiency is very important in wireless power transfer, and we can improve the power efficiency in many ways. But I think there is physical limits. Yeah, for example, if we want to transfer the power over a very large gap, then the efficiency cannot be high. There is a theoretical maximum power efficiency. Yeah, so what we can do is try to achieve the maximum point, but the maximum point cannot be improved to 100%. So that's a power efficiency issue of wireless power transfer.
I have another question. Do you know if there are works related to the effect on the health on the driver or the persons of the wireless charging, since it's an electromagnetic field?
Yeah. I think you are mentioning the safety issue of wireless power transfer.
In general, not of your.
It is also sorry?
In general, not your work, since I do not know if there is some work in that field on the effect on the health of.
Sorry, I cannot.
I think the question about is there any work done regarding the health and safety issue of the driver? You are driving on the EV charging all days, and it's a big charging stations. Will it impact the health of the driver or exposing to such EVs fields in the long durations? Any works are done here?
I cannot hear the questions very clear. I think you are mentioning the safety issue. For safety issue, the magnetic exposure should be controlled and should be limited to a very low level. I'm not sure.
Okay, thank you. It's enough for me. Thank you. Any other questions?
Thank you, Professor Conti.
Yes, Professor Conti, thank you. I have a question, Professor Huang. I think it's a very good work you made. Just one question. What is the current standardizations related to wireless charging for EVs? Because we know wireless charging have been used for mobile devices like the Qi charging standard. But I'm not very familiar with the charging standards for the EV wireless charging at the moment.
Yeah. Actually, there was some standards. The wireless EV charging standards, international, and also in China there is a national standard. But nowadays wireless EV charging is not widely used. I think the reason is the cost, the volume for wireless EV charging is very high, still very high. And so that's why we try to reduce the copper usage, and we try to simplify the control, and we try to increase the spacing distance between the adjacent magnetic couplers in dynamic EV charging. But I think the cost is still a very big problem if the wireless EV charging goes to the market.
Yeah, thank you. I mean, the reason I'm asking standards, I mean, that can refer to Professor Conti's question about the safety and health concerns. So, for example, we have something called a radio frequency interference, RFI problems. So that is to make sure different components or devices or systems, they do not affect each other. I mean, there are many standards in this case, but for EV, wireless charging and health concerns, I think some standards activities in this area might be quite useful, if there's none yet.
Yeah. Just as what I mentioned, there was some standards, and in these standards, I think we can satisfy the requirements of these standards. But however, the cost is still very high. So I think that's the key problem of wireless EV charging. Yeah, not the standard issues.
Okay, thank you, Professor.
For the requirements in the standards, I think that's fine. Yeah. Thank you.
Thank you. If there is no other questions, for my side, I will thank you the speakers. They both were very interesting, and I think that this can be a good opportunity to be in contact. Everybody who attended these presentations. So I would like to thank you, the two speakers, and Fabrizio Lamberti for organizing all these technical presentations. So thank you for everybody.
Yeah. Thank you. Okay then. Yeah, take care. Bye-bye. Thank you.
Thank you.
Thank you. Bye-bye.
We can leave now.
Thank you.
Okay.
See you.
Thank you.
See you.
you.
Bye.
Thank you all. Thank you
See
for
you.
the TC officers. Okay. Okay.
Thank you.
Then let's end this technical talk. Thank you all.
Bye-bye.